Hi, in this video we want to talk about using an external crystal, a small piece of electronics that will let us make our computer chip run at very much more precise uh, values of the clock. The built-in clock is good to 1% or 2. We would like a few more significant figures when we talk about what the frequency of the internal clock is. Now, an external oscillator comes in many different packages. This is one of them. This is the one we'll be using. You can see that this guy has 4 pins. It's got really nothing to tell you much about it, except for the fact that on this guy, there's a bit of writing that tells you that it's 8.000K. The K tells you it's good to 30 parts per million, which means it's much more precise than what we're using. It also has the manufacturer's sort of shorthand code for you to Google and find out the data sheet for this guy. Now when it goes into your breadboard, like on this example that I have done up already here, you make sure that your crystal or external clock straddles the gutter. Right? So that means the 4 pins are in 4 different rows. In one corner, connected with the white wire, we've got the signal output, and we've got this white wire that goes to pin 9 on the PIC. Over at this end, we've got a wire to ground, and on the other side, let's see if I can get this right, there's a power connector for the oscillator chip. It needs to be powered up too. And as well, it's a little hard to see it, there's a teeny tiny capacitor. And the job of the capacitor is to reduce the effects of any external noise on your circuit to keep the precision quite high. The 4th pin is not connected. There's no connection to this pin. Okay. So that's it. That's all we're going to be doing. And once we've correctly modified the software, that'll let this run at 8 megahertz or other speeds to not 1%, but a fraction of a percent. It'll be extremely precise. And usually you want a great deal of precision whenever you're measuring external signals. We don't actually have to make a lot of changes in software to use an external crystal. We do have to make sure, however, that we make sure everything is wired correctly. Improperly wired external clocks or crystals will cause us big problems. So right here, what I have is a picture of the front face of the crystal. You'll notice this little circle here. This identifies where pin 1 is. Right? Over here, it's pin 4. It's not marked. Pin 5 and pin 8. This is what the other side of the crystal looks like. Down here, we have the pin-out diagram. I've got it turned sideways because that's the way I use it to straddle the gutter, because I want pin 5 to be the closest pin to pin 9 on the PIC. You want short wires. It reduces the amount of noise that you could get and gives you a purer, higher precision signal. This says what to do with the different pins. Pin 1, which you can tell by the sharp corner, which isn't as visible in the diagrams, but there's a sharper corner right here. The other corners are rounded. You can see the rounded corners easily enough. Pin 1 is not connected. Pin 4 goes to ground. Pin 5 is the signal. which goes to clock input, which is pin 9 on the PIC. And the other side has two connections, one to ground and one through a small, 8 is connected to power. That's what powers the chip. And as well, to reduce noise, we've got a small capacitor connected between that row and ground. That should be all we need to make the connections work. Now, here in the pin out diagram for the PIC, you can see pin 9 is CLKI. That's short for clock in. Okay? That's what we want to connect to. When we connect in this external clock, we'll still be using pin 10 as clock out. So if we connect up to an oscilloscope, we can read the frequency of the now new internal clock, right? Or more precisely, of the peripheral frequency clock. The only software we need to change to use the external crystal is in the configuration bits file. Here's the section that's important. In red, the first thing that you got to make sure is that you're using the external clock. That's what the EC stands for. So that one, it's usually off, so we want it to be EC. And then the second one that you have to make is this FN-OSC, which we've used before to change the frequency of the chip. And we're telling it to use the primary input oscillator. Okay. So PRI. Once we have that set up accurately, when we start the PIC up, it'll be operating at whatever the frequency the external clock is, right? So if it's 4 megahertz, the chip will act at 4 megahertz. If it's 20 megahertz, the PIC will run at 20 megahertz. We actually get to play around a bit more than that. We can use the phase linked looping effect to actually have different speeds. Okay. One of the things when we're using the external clock, though, we should be modifying this configuration bits, and not to get confused with the standard one we're using. Call it something like EC configuration bits. Then you know you're using the external clock. The other way you can modify the external clock, again, you need to tell it you're using the external clock, but now this one is the external clock with PLL, phase loop linking. I can never remember that anagram, okay? Or abbreviation. A couple of things to remember. This guy, you choose this division such that the whatever crystal you're using divided by that number is between 4 and 5 megahertz. Otherwise, things will not work properly. Once you've got that set up, then whatever multiplier you use in divisor gets multiplied by that overall clock. And so you can have many different choices for this. Okay? So if you want to modify the clock in your code using PLL, that's easy. We've got this osconfig function in plib, right? And this one we don't change. This just says use PLL. We need to know what x is. The choices of x go from 15 down to 24. You'll notice there's a 22 and 23 are missing. And then osPLL post, right? And post can be 1, 2, 4, 8, 16, 32, 64, 256. This guy gives you the lowest, right? So if you use 15 and 256, that'll give you the lowest, right? The external crystal we're giving you is 8 megahertz, right? So to get down between 4 and 5 megahertz, we need to divide by 2. That's it. It's that simple. Let me just show you some of the code, right? So here is my code. I'm going to go to my header file and show you the configuration. move this down a bit, right? So here I'm using pre-PLL, and here's POSCMOD, I'm using EC. And I've had to choose this guy to be 2. And I've set these guys up so that it's 8 divided by 4 is 2 times 16, right? 8 divided by 2, sorry, is 4 times 16, 4 divided by 8. So this setup is still 8 megahertz, what we're used to. In the program, right, I've included EC configuration bits, right? And here's me using the code, right, this osconfig function to get the right combination. Here I'm using 24 and 16. So the formula is 8 divided by 2, that's 4, times 24 divided by 16. So 4 times 24 divided by 16, that works out to 6 megahertz. Remember, if you're going to be using configure UART2, make sure you get the right value, or it's going to look like noise on PuTTY. That's it. Right? It's that simple to wire up the chip to use an external clock. Thanks. Bye for now.